Yes, I can hear you.
Okay, that's great. Okay, so thank you for the organizers to inviting me here to come to Turkey. So unfortunately, I'm the only of this iron-based session which is here in person. So it would be nice to discuss. Well, this is the outline of my talk, and since this is a session on properties for application, I will focus here on properties which are important for applications. And in the first part, I will talk about pinning, and I will try to outline that here is a very relevant parameter for applications, the bearing current density, because it sets the basic availability of the material for high currents. So, and then you can separate this JC then also in pinning efficiency, which is also important, but this pinning efficiency can be tuned by preparation, but the bearing current density is more or less given. So in the second part of my talk will be about granularity effects. I will show that if you have untextured material, you have to model this as a network as Josephson coupled grains, and also then say a few words about the requirements in terms of texture for certain applications. And finally, I will show a few recent results here on coated conductor made of the 1-1 system. Switch? Would you switch?
Yes. Switch.
Now, okay, before I start, I have to acknowledge my colleagues from the Dom Institute von Ustem in Vienna, and I also have to mention the ISW in Dresden, who provided us with the coated conductors, and finally the single crystals I will refer to. Okay, let me start with neutron irradiation experiments, and here the salient point is that if you start with pristine materials, so here on the bottom left panel you see different 1 to 2 materials, and in the pristine state this is the volume pinning force as a function of magnetic field. This is quite different depending on the compound, but after the irradiation you find the similar behavior. All this curve on one master curve, meaning that you really have now a benchmarking defect structure which is the same in all of these compounds. This was also observed in the rare earth components, for instance, in the coated conductor. So pinning is very strong there, and in the unirradiated sample you see here, these are the solid symbols. You see that there's a spread of properties, but then after the irradiation you find the same behavior, that it all collapse on one curve. Okay, and now this neutron irradiation allows to compare material, and this is a self-filled JC at low temperatures and self-filled, and you can see here two things. The one is that you have a large, you have quite a huge difference here between the materials, with the lowest value for the 1-1 compound here and the highest with YBCO. This is a factor of 50, although you have now the same defect structure. And the reason here is the bearing current density, which is given by Ginsburg Landau theory according to this expression here. And if I now normalize JC by the bearing current density, I get the so-called pinning efficiency, and then everything becomes sound. You see that all these materials collapse to 2 to 4% here of this pinning efficiency, meaning that now we have a similar benchmarking defect structure, and then you get, of course, also the same behavior. So now the slide anymore here, so thanks again. Okay, and the other important point I want to stretch here is that in real optimized conductors you can have a pinning efficiency around 15%, better than in this neutron irradiated system. But this is sort of a final limit. This is also theoretically expected. Okay. Then in particular in the 1 to 2 case, we found a very interesting correlation between TC and the bearing current density, so which is shown here. here this is the same data, more or less, but now for more different doped 1 to 2 crystals, and you see that if you plot JC as a function of TC, you find here this linear behavior on a double logarithmic scale, so which says that this is just a power law between JC and TC, and this is quite well expected from the bearing current density, which can be rewritten as the fraction between PC and lambda, and using the Uhr relation for the superfluid density. And here what was found in the in the 1 to 2 compounds for the thermodynamic critical field, you end up exactly with the observed behavior. This is quite interesting and shows that we really have this proportionality between JC and the bearing current density. Okay, now let me say a few personal views of the application prospects of the iron-based superconductors, and therefore I want to compare here some important properties of the iron-based superconductors here on the right-hand side, and the other technical important superconductors on the left-hand side. And of course, it's obvious that the C is much better than in the low-temperature superconductors in the iron-based stuff, and of course not as good as in the cuprates. And this is very similar to the situation of BC2. BC2 is of course also here quite favorable compared to the low-temperature superconductors. And finally, let me also comment here on the bearing current density, and this is of course quite interesting. Of course, YBCO is here, let's say, this champion, and also niobium-13 is quite good, and the iron-based superconductors can compete with these high values in principle. The only exception is the 1,1 compound, which I would say is not so promising for the applications in this respect. Okay, but now let me just briefly say what current do you actually need for applications, and I will also refer to the bearing current density again here. As I said, you can have about 15% of the bearing current density in cell field, and in field, you know that normally the critical current are suppressed by another order of magnitude, even more, I guess. So I would say you need at least a factor of 70 between the bearing current density and JC. So, and then what do you need, for instance, in magnets applications to have a fairly compact winding pack? You should have a gradient of 1 Tesla per centimeter at about 5 Tesla per centimeter, which corresponds then to 5 times 10 to the 4th amps per square centimeter. And now, of course, this is engineering current density, and going here back to the JC, if you have a wire with a high filling factor, you would then end up with the requirement for a bearing current density of 7 megaamps per square centimeter. On the other hand, if you plan to make a coated conductor with have a filling factor of, let's say, 2%, you need a very high bearing current density. And looking here again at these values, you see that only 2 compounds of the iron-based superconductors would fit this requirement. But I'm not sure. I'm not aware of any work with coated conductors with this compound, because they are quite complicated to grow. And it's also quite obvious why YBCO is the only reasonable candidate so far for making coated conductors. So, in my view, for the iron-based superconductors, you just have application prospects if you have a wire, and it should, of course, be cheap to be able to compete with niobium titanium, for instance. Okay. So now let me come to the second part of my talk, which refers to polycrystalline materials. And as I already mentioned, there you have to model this as a network of weakly coupled grains, and this can be seen here just for this famous bicrystal experiments, which show here this exponential decrease of its misalignment angle, and you end up here at Josephson junctions at high angles. And in a non-textured material, all grain boundaries, or not all, the majority of grain boundaries have angles above 45 degrees. So this is quite consistent with the observation that you really find this hysteretic behavior of JC and this asymmetry in magnetization measurements. This is just a signature of this Josephson-coupled grains. And then one of my PhD pointed out that refining the grains could really be very beneficial for increasing the field dependence. So this is just an effect here of this particular Josephson physics. And if you see here this strong increase, if you decrease the grain size by a factor of 10 of the JC in field, this is true for the increasing and decreasing field branch. Okay. So then I made also some modeling of the influence of texture, and this is all based here now on this data on the bicrystals again. You will see here then, if you now assume that you have a distribution of your grain orientation, then you will find, of course, nevertheless a similar behavior. And let me start here with biaxial texture. So here on the x-axis is the average misalignment angle. So we start here with biaxial texture, that all grains are aligned, and then you see that the iron-based superconductors, the black squares here, have a much weaker decrease with misalignment angle. Nevertheless, even at about 12 degrees, you lose 1 order of magnitude in JC. So there's, I would say, not too much better situation than in the cube plate. On the other hand, if you have just uniaxial texture, this is now here, you see that this is just a suppression if you have perfect uniaxial texture, meaning that all grains are aligned with their z-axis and no in-plane orientation at all. You would find just a factor of 10 suppression in the iron-based superconductors, while you have about 2 orders for the cuprates. And if this compares then to the real critical current density, you indeed can come up here with uniaxial texture above this application threshold here in the iron-based superconductors. However, for in-field applications, I guess you would end needing for the need for biaxial texture, at least if no one has a good idea to increase the grain connectivity. So it's the wrong direction. So now let me show just a few results on our 1-1 on a technical substrate. So this is a 200 nanometer PLD film on IBET MgO, and we etched a 1 millimeter spot for whole probe microscopy. And so you can see here the result. This is a fairly homogeneous beam profile. It's not as perfect as you would see in YBSO, for instance. And also, if you invert this and calculate the current, you have here some inhomogeneities. But of course, this is reasonable for large currents, large microscopic. On the other hand, if you do this on rabbits, the situation is different. You already see in the optical microscope here some dark spots on the substrate, and if you do then the scanning hole probe mapping, again, you see that you have a more inhomogeneous profile with many maxima, and this is just a signature that the current meanders around some of these dark grains here. And to understand this better, so this is an overlay, you see really that there's an excellent correlation between the position of these black spots and the current flowing in between. And we looked here what happens at these black currents, and so this is now an SEM picture of just a few grains, and we made here a lamella in between a good grain and a bad grain, and you see the SEM also here, the surface of the bad grain is different, and we have here this boundary, and then we put out the lamella and put it in the TEM, and this is what we observe here. On the good grain side, you have a very homogeneous layer, the 1-1 compound, while on the bad grain, you have on the bad side, you have here a very inhomogeneous growth. So it doesn't seem to be related to the buffer layer, which seems okay on both sides. If you finally then do some dark field images, you already see that you may have different grain orientations, because if you change the diffraction point, you see different areas, which is not the case here on the good side of the boundary. And finally, to look closer at this, we made some transmission Kikuchi diffraction, and what we observed here is that the substrate here, the tilt of the out of plane of the z-axis is 1.9 here on the good side, and on the bad side it's up to about 5 degrees. And then this obviously is very detrimental to epitaxial growth, because see here now that we find both an out of plane tilt of about 55 degrees, and also here subgrain structure with an independent intercept. Okay, and this brings me to my conclusions that I guess the chip wire is the only way to go for applications of IBS for power or magnet technology. And I guess there are two ways. One is to try to get uniaxial texture, but might be lead to similar complications than the cuprates. And you would, in any case, think you need biaxial texture for application, or you find a way to improve the grain coupling similar to what was observed in the cuprates if you do some overdoping of the grain boundaries, and then a grain refinement could be very beneficial for improving the field dependence. So thank you for your attention.